Derivatives and rates of change, Part 1. It's finally time to find the slope of a tangent line at a single point, which is what we were trying to be able to do starting from the very first part of Calc 1. So we noticed that the slope of a secant through x f of x and a f of a, so where this is point A, and this is some other point, so we keep having our point at a f of a, and we look at what happens to the secant line, so through that a f of a and some other point on our function, and we're looking at what happens as that point gets closer and closer to a f of a, and what happens to the slope of the line, the secant line, through those 2 points. And we've noticed that as x gets closer and closer to a, so just whatever our other input is, the slope of the secant line gets closer and closer to the slope of the tangent line through the point, which we can kind of sketch a picture of, but we're still not quite sure what it is. It's some sort of slope, but the secant line is getting closer and closer to looking like our tangent line as x gets closer and closer to a. And we've talked a lot about this approaching thing, especially as x approaches a, which means that we might be able to find some sort of limit definition of the slope of this tangent line. So the tangent line to the curve y is equal to f of x at the point P, a f of a, is the line through P, so through that point a f of a, with the slope m is equal to the limit as x approaches a of f of x minus f of a over x minus a. And that just means if we have some function and we have the point a f of a, and we're just looking at some other point on here at x f of x, as x gets closer and closer to a, so as x approaches a, the slope between these 2 points gets closer and closer to being the slope of the tangent line. Through, specifically, a f of a. And this is one of the first ways that we define it, but there's actually another way to define the slope of the tangent line using a limit. And that's where we look at this thing called h. So if we have a function, and we're looking as x approaches a, we'll call this x, and we look at the distance between 2 different points, so we have x plus h here. That means that we have 2 points, x comma f of x, and x plus h, comma f of x plus h. And we look as this x plus h gets closer and closer to x, where h is the distance between x and x plus h. So that's essentially looking at as h approaches 0. And h is actually x minus a, so the distance between x and a. And we're looking at the distance becomes 0. The derivative of a function f prime of x is equal to either of these limits that give us the slope of a tangent line. So that means that the derivative of a function is another function that outputs the slope of the tangent line at a point. So if we're like, well, we don't want just the tangent at one point, we want to be able to find the slope of the tangent at any point on this function, then we'd find the derivative so that we could get that slope. So we've talked about the average rate of change and instantaneous rate of change before, where we found the average rate of change by finding the slope of the secant line. And we've said that the instantaneous rate of change will be the slope of the tangent line. But up until now, we didn't have a way to actually find it. We were approximating the slopes of the tangent line, so we were approximating the instantaneous rate of change. Now, we actually know how to find the instantaneous rate of change. It's the derivative of a function, which is defined as that limit as the average rate of change as the change in x approaches 0. Rates of change apply to almost every field, particularly STEM fields. So anytime you're measuring something that changes with respect to something else that changes, which is frequently time, we do a lot of things with like distance versus time, especially in physics. And that's one of the many reasons why almost every STEM major is required to take calculus, at least that first section of calculus that deals with these tangents and these slopes of tangents, these rates of changes and derivatives, which essentially are just different ways of saying the same thing. So a frequent application of this is s of t, the position function, where the average velocity from t to a is equal to just this average rate of change. So s of t minus s of a over t minus a. And the velocity, and this is the instantaneous velocity, but we'll just call it velocity, is equal to s prime of t, which is the limit as h approaches 0 of s of t plus h minus s of t over h. Notice how we're using the definition that has the h. Although we could use the other definition, this is the most commonly used definition because it ends up being a little easier to simplify and work with for many problems. An important reminder, please remember that the equation of the line through the point x1, y1 with a slope m is y minus y1 is equal to m times the quantity x minus x1, because we will be finding many, many equations of tangent lines through a specific point. So we'll be using this equation in order to do that, where m will be equal to that limit as h approaches 0 of f of x plus h minus f of x over h. At least when we're finding the equations of tangent lines, which is one of the big purposes and goals of calculus.